Welcome. This is Coach Dorf. We're in section 5.3a, and we're looking at some homework examples. In these examples, we're supposed to find the derivative of a certain set of functions. So let's begin. What do I notice about all the functions I have here? All these functions are written as integrals, and I'm taking the derivative of those functions. So I'm taking the derivative of integrals. That should bring to your mind the idea of the fundamental theorem of calculus part 1. And what does the fundamental theorem of calculus part 1 say? It says that if I'm taking the derivative of an integral and the function I have that I'm integrating, so the function after the integral sign, if that's a continuous function, then the derivative of the integral is just that inside function. It's called the integrand, the function after the integral sign. It's just the derivative of the integral then will just be that integrand, and I replace the dummy variable, in this case t, with the value x. Let's look at this specifically in these examples here. So in part A, I have f of x equals the integral from 0 to x of e to the negative t squared dt. We want to find the derivative of x. So that means we want to find the derivative of this integral, 0 to x of e to the negative t squared dt. So notice we have a derivative and we have an integral sign there. Also, notice that the limits on the integrals, the numbers on the integrals are 0, and then we have the variable x there at the top. The fundamental theorem calculus then says because e to the negative t squared is continuous. And why is e to the negative t squared continuous? Well, remember the restrictions we have are that if we have like a fraction, a function is like a fraction or a rational expression, so it has a numerator and denominator, that the denominator can never equal 0. Well, we don't have that in this case. Also, the other restrictions are that we would have a square root, or if we had a log function. Well, this doesn't have either of those, so there are no restrictions. So this function e to the negative t squared is continuous from negative infinity to infinity. So it's always continuous. And my limits on my integration are 0 to x. So the fundamental theorem of calculus says that I'm going to take my integrand function e, and I'm going to write minus x squared there. And so in other words, I'm replacing the dummy variable t with the x that's at the upper part here of my limit of my integral sign. Notice that this has to be a constant, and it can be any constant, but 0 is a constant, so that works. And this is just my variable here. And that variable relates to the f of x, right? We have an x here, that's the variable there. All right, so that's what we have in this case for part A. Now let's look at part B. Part B is slightly different. Here we're going to have the function g of x, and now we're going to have the integral from 0 to tan x of e to the negative t squared dt. So my difference here, of course, is that my upper limit on the integral sign is a tan x instead of just an x. So again, what we're trying to do is we're trying to find the derivative of this function. So we're finding the derivative of the integral from 0 to tan x of e to the negative t squared dt. Again, I've got the same integrand function, e to the negative t squared, so we know that's continuous, so I can use the fundamental theorem of calculus. And I'm just going to go ahead, like we did before, I'll start writing my integrand function. I'll go e to the negative tangent x squared there. But because the limit on the integration here, it's tan x and not x, I have to then multiply this by the derivative of that function, tan x. And so what I get in the end is e to the negative tan squared x times, and the derivative of tangent is secant squared. So I get that as an answer. All right. Now you may wonder, why didn't we have to do that in the first problem in part A? Well, we did, but we didn't do it explicitly. In that case, if we would go back and do this one, part A here, I'm going to write this in blue at this part here. I could have done the derivative of my variable function x. Well, what's the derivative of x? That equals 1, and I'd still get e to the negative x squared. So let's look at the last one, letter C. And in that one, we have the function g again, and that's going to be the integral from from tan x to 0, right, of e to the negative t squared dt. And again, I want to take the derivative of that. So I'm taking the derivative of an integral. You get that right here. That's tan x on the bottom and 0 on the top. Again, I notice that my integrand function, e to the negative t, is continuous everywhere. So I can apply the fundamental theorem of calculus here. And when I do that, the difficulty is here now, I don't have the constant at the bottom of the integral sign as the bottom limit, and I don't have the function with x as the top. So what we need to do is we need to use one of the properties of integrals, and that is I can switch the order of the integral here. I switch the limits, so I can put 0 on the bottom and tan x on the top if I put a negative out front. Notice this relationship here. If I switch the tan and the 0 here, I have to put a negative out front. So applying that to taking the derivative here, I'm going to have a negative of the derivative of the integral from 0 to tan x of e to the negative t squared dt. And then when I apply the fundamental theorem of calculus here, I get negative, and then I get exactly what I had in part B, because it's now the same as that. So I'm going to have e to the negative tangent squared x times secant squared x. All right, hope that helps.